Welcome to Spring LIB.
Hello everyone, today we're doing chapter 18, problem 10, and this problem asks us to draw a stepwise mechanism for the following intramolecular Friedrich-Crafts acylation from the starting material to product here. So what we see is that we have some sort of derived benzene groups, electron withdrawing derived benzene groups, a benzene ring here, and then we have some sort of acyl group here, and we know that we're going to have some sort of intramolecular cyclization occurring at this carbon here. And a good way to know how many carbon is going to be your intramolecular cyclized group is just count the carbons. We have 1, 2, 3, 4, 5, 6 carbons. We know the chlorine will leave as depicted in the product, so we know that we'll have a 6 carbon group cyclical moiety being formed, or in other words, we'll have a cyclohexane being formed. So the mechanism of this is, well, typically we have the benzene ring as our nucleophile, which it still is. This pi bond here will act as our nucleophile. And then we have a separate molecule, which is going to be our electrophile, that being the acyl group. But here, both the nucleophile and the acyl group are on one molecule. But the steps don't change. We still need to form our electrophile, because this is an electrophilic aromatic substitution reaction. And then once the electrophile is formed, we have a positive charge, and our nucleophile can attack this electrophilic carbon center here. So let's first add our Lewis acid catalyst, aluminum trichloride. We'll have the chlorine group attack this aluminum with its lone pair electrons. And now we're forming our first intermediate product. And because we use the lone pair electrons from chlorine to attack aluminum, aluminum gained 2 electrons. So now we have a negative charge in aluminum, and this chlorine lost those 2 electrons, so we have a positive charge in the chlorine. Now what we know is that our chlorine is not happy to be positively charged, so it wants to be neutral or negatively charged. So what's going to do is going to pick up those 2 electrons from this sigma bond between this carbonyl carbon and the chlorine. It's going to pick up those 2 electrons, and now in the process, it's going to form now our carbocation intermediate, and let me draw like this, and our conjugate base. So now that we've formed our electrophile, we can actually have some sort of resonance stabilization with this, with oxygen, those 2 electrons of oxygen going down to make 4 bonds on this carbon and moving the carbocation, or the positive charge, onto the oxygen nucleus. And we can just show that resonance structure, but that doesn't really help us with our mechanism. That just shows the stabilization of this particular intermediates. But from now, with the positive charge on this carbon atom, we know that we need to add this molecule onto this carbon here, and we can confirm that because this benzene group is an alkyl substituted benzene group. It has this carbon that's directly bonded to it. So because we have an alkyl substituted benzene group, we know that alkyl groups are ortho and para directing. And not only that, we have 2 ortho positions. So we can attack on this side and on this side. But in this situation, we'll attack on this ortho position here. So we know that the 2 electrons from this pi bond will go through this carbon nucleus, attacking this carbon to neutralize the carbocation. Oh, let's draw that better. There we go. So now we have this bond here is the new bond that was formed. So now we know that this carbonyl group will be here, but we're going to have a carbocation being formed at this carbon because we took away those 2 electrons from this carbon here. So we're going to have a carbocation here. So what's going to happen is that now we need to move this carbocation around. Particularly, this moving around means that we're having resonance structure. So we can actually move this by moving these pi bonds. And this just shows that the resonance stabilization of this molecule, but doesn't actually help in our mechanism. But we can show the resonance stabilization like we did in the previous problems that we did. I think it was problem 2. We showed that these pi bonds can move around to have 3 resonance stabilized forms, one of them having the carbocation on this carbon, showing the inductive stabilization from the alkyl substituted group here. Therefore, that's explaining why it's actually ortho and para substituted and directing. But what we have to continue the mechanism is we have our Lewis conjugate base of our Lewis acid, and we know that because this was an acid catalyzed mechanism, we must reform the acid catalyst. So what we can do is that this aluminum has a negative charge and it's not happy about that. So what we can do is use those 2 electrons to pick up this hydrogen, making a bond. We make a bond, we break a bond. So the sigma bond will break to reform aromaticity in the ring, lower the energy of our product, and form this product of interest shown here. So we're reforming our benzene ring now. We're reforming the aromaticity of our benzene ring by the addition of this pi bond here. And now we are forming HCl, and we're reforming our acid catalyst here, and our product of interest shown here.